On this page, we are entering the next major part of this section, which is stimulated and spontaneous emissions using Einstein's A and B coefficients. In the previous subsection, we discussed the density of states for photons. That discussion is important because in a broad spectrum electromagnetic field, light is not described by just one photon frequency. Instead, the radiation field contains many photon modes. Each photon mode is specified by a photon wave vector and a polarization state. Now we will use that photon density of states to discuss three fundamental optical processes: absorption, stimulated emission, and spontaneous emission. The central goal of this subsection is to connect Fermi's golden rule with Einstein's A and B coefficients. Einstein's B12 coefficient describes stimulated absorption from a lower level E1 to an upper level E2. Einstein's B21 coefficient describes stimulated emission from E2 back to E1. Einstein's A21 coefficient describes spontaneous emission from E2 to E1, which can occur even without an incident photon. So the structure of our discussion is as follows. First, we write the stimulated absorption rate in terms of the photon spectral density. Then we write the corresponding stimulated emission rate. After that, we introduce spontaneous emission and derive the relation among A21, B12, and B21 using detailed balance at thermal equilibrium. Finally, this discussion will prepare us for the next subsection, where we derive the optical gain and spontaneous emission spectra in semiconductors. At that stage, the simple two-level picture will be extended to band-to-band transitions in a semiconductor. The important point for now is that this subsection is mainly for a two-level system derivation. We are not yet summing over all electron wave vectors in a semiconductor band structure. The summation that appears in this subsection is primarily for photon modes. On this slide, we define Einstein's B12 coefficient for stimulated absorption. We begin with a discrete two-level system as shown. The lower level has energy E1 and the upper level has energy E2. For absorption, the system absorbs a photon and makes an upward transition from E1 to E2. The required photon energy is E21, which is equal to E2 minus E1. Because the incident field is not necessarily monochromatic, we must consider all photon modes in the radiation field. I will label the photon wave vector by Q. A photon mode with wave vector Q has photon energy h bar times omega Q. Using Fermi's golden rule, the transition rate contributed by one photon mode is proportional to 2 pi divided by reduced Planck constant times the absolute square of the matrix element times the Dirac delta function. The delta function enforces energy conservation. It selects photon modes whose photon energy matches the transition energy. For stimulated absorption, the rate is also proportional to the number of photons already present in that mode. This is why the photon occupation factor N sub pH appears. More photons in the resonant mode means a higher probability of absorption. We then define B12 equals 2 pi divided by the reduced Planck constant times the absolute square of the matrix element, where H sub 21 prime plus represents the matrix element associated with photon absorption. The coefficient B12 measures the stimulated transition strength associated with stimulated absorption. Therefore, after summing over photon modes, the absorption rate per unit volume can be written in the form shown here. The factor of 2 comes for 2 possible photon polarizations. Now we use the photon density of states. The quantity in the square brackets, in fact, is the density of states for photons, and it is denoted by capital N of e to 1. It is the number of photon moles per unit volume per unit energy at photon energy e to 1. It has units of 1 per cubic centimeter per electron volt. The product of the density of states for photons, capital N of e to 1, and the photon occupation number per mode, which is N sub pH, gives the photon spectral density, capital S of e to 1. It is the number of photons per unit volume per unit energy interval. This allows us to write the per unit volume stimulated absorption rate compactly as B12 times capital S of e to 1. Finally, if the two-level system represents electronic states, we must include the occupation probabilities. Absorption can occur only if the lower level is occupied and the upper level is empty. Therefore, the probability factor is F1 times 1 minus F2. So the absorption rate per unit volume becomes the equation shown here. This is the key result of this slide. We now step into stimulated emission in a two-level system. Before diving into any mathematical expressions for this process, I'd like to introduce the physical picture of stimulated emission. In this process, the system initially has an electron in the upper level E2. An incoming photon with energy h bar omega interacts with the electron and stimulates it to make a downward transition from E2 to E1. When this happens, a second photon is emitted. The important point is that the emitted photon is not random. It has the same energy, phase, polarization, and propagation direction as the incoming photon. So before stimulated emission, there is one photon in the optical mode. After stimulated emission, there are two photons in the same mode. These two photons are coherent with each other. This is the microscopic origin of optical amplification. One photon stimulates the emission of another photon into the same optical mode. If many excited atoms or carriers are present, this process can multiply the photon number in that mode. This is also why stimulated emission is central to lasers. A laser doesn't rely primarily on random photon emission. It relies on stimulated emission where photons are emitted coherently into the same optical mode. This produces light with high directionality, narrow spectral width, and strong phase coherence. However, stimulated emission can dominate only if two conditions are satisfied. First, there must be a significant photon population in the optical mode. Second, the upper level must be sufficiently populated compared with the lower level. We will quantify these two conditions in the following slides. Now we write stimulated emission mathematically using Einstein's B21 coefficient. The transition is now downward from E2 to E1. The photon energy is still equal to E2 minus E1. The equation for the downward transition rate per unit volume is in the same form as that for the per unit volume upward transition rate as we discussed earlier. Like what we did before, we defined the Einstein coefficient for stimulated emission as B21 equals 2 pi divided by h bar times the absolute square of the optical matrix element. Here h sub 1 2 prime minus is the matrix element associated with the emission part of the interaction Hamiltonian. The coefficient B21 measures the stimulated transition strength associated with stimulated emission, and it has units of electron volt per second. We also note that for both absorption and stimulated emission, the relevant photon energy is always equal to E2 minus E1. So the direct delta function enforces the same energy conservation as found in the upward transition rate. The quantity in the square brackets is therefore still the photon density of states, denoted by capital N of e to 1. For stimulated emission, the incoming photon mode stimulates the electron to emit another photon into the same mode. Therefore, just like stimulated absorption, the rate is proportional to the photon spectral density, denoted by capital S of e to 1. By including the occupation probabilities, we obtain stimulated emission rate per unit volume, as shown in this equation. The per unit volume stimulated emission rate can be further expressed as the stimulated emission rate per unit volume per energy interval times the spectral width dE of the emitted light centered at energy e to 1. Because the small case r sub 21 superscript stimulated is a per unit energy interval quantity, it can be used to describe the stimulated emission spectrum, as we will discuss later. Also, the factor F2 means the upper level must be occupied. The factor 1 minus F1 means that the lower energy level must be empty. For electronic transitions, this is required by the Pauli exclusion principle. So absorption and stimulated emission share an identical mathematical form. The main difference is the direction of the transition and the occupation factors. This result also shows why stimulated emission requires photons already present in the optical field. Without photons in the resonant mode, the photon density of states, capital S of e to 1, is 0, and stimulated emission does not occur. Spontaneous emission, on the other hand, can occur even when there is no incoming photon. That's the topic of the next slide. This slide introduces spontaneous emission. In spontaneous emission, the electron is initially in the upper level E2, and it makes a downward transition to the lower level E1 spontaneously or automatically. During this transition, a photon is emitted with energy h bar omega equals E2 minus E1. The crucial difference from stimulated emission is that spontaneous emission doesn't require an incoming photon. It can occur even when the external radiation field is absent. Therefore, the spontaneous emission rate per unit volume is independent of the photon spectral density. We then write it using Einstein's a to 1 coefficient as shown in this equation. The coefficient a to 1 represents the spontaneous emission rate of one occupied upper level into all available photon modes. In other words, it already includes the effect of the available photon modes into which the photon may be emitted. The factor F2 means that the upper level must be occupied. On the other hand, the factor 1 minus F1 means that the lower level E1 must be empty. The per unit volume spontaneous emission rate can also be expressed as the spontaneous emission rate per unit volume per energy interval times the spectral width of emitted light near the transition energy e to 1, and it is denoted by dE. Physically, spontaneous emission is more random than stimulated emission. The emitted photon may go into many possible directions and different polarizations. Its phase is not locked to an incident field because there is no incident field stimulating the emission. In contrast, stimulated emission emits into the same optical mode as the stimulating photon. This randomness is one reason spontaneous emission is usually associated with incoherent light, whereas stimulated emission is associated with coherent optical amplification.